2.6.
No, that's initial velocity. Acceleration. After it is launched, what are all the forces acting on it after it has been launched?
Wait.
Anything else? All right, so it has weight. If weight is the only force acting on it, what is the acceleration?
As in like positive or negative?
Well, we'll need to do that at some point. Do you want to go ahead and do that part?
Negative.
Okay. Sushil beat you to it. Sushil just established up is positive. All right, so what's the acceleration? If the only force is the force due to gravity, what is the acceleration?
9.8.
It would be the acceleration due to gravity. So my acceleration is 9.8 meters per second squared. That's going to be equal to my change in velocity. Oh, there is an issue there. This is incorrect. And I'm not doing we live in Winston-Salem, so it's a little bit off. What's wrong with this? And if you don't like that this is off, you can blame Sushil.
It's negative.
Yeah, it's negative. Acceleration's down. All right, what's the change in velocity? That's the initial velocity. What is the final velocity? We're trying to figure out how high up it's going to go. So when it reaches that highest point, what is the velocity? So therefore, what is the change in velocity?
Initial velocity. Initial v minus final velocity.
So close. All right, so final change in velocity. I got final and initial. Is it final minus initial or initial minus final?
Final minus initial.
So V final minus V initial. And that's 0 minus 2.6. So it's negative 2.6 meters per second over time. So the math problem we're working with, I have minus on each side, I can get rid of it. We're dealing with 9.8 over 1 is equal to 2.6 over time. How do you solve that? There's more than one way.
2.6 over 9.8.
Yeah. I can always move things across the diagonal if I have two fractions equal to each other. So I can flip those around. So one way would be to, in essence, put the purest in there, multiply both sides by time over 9.8. And you end up with time is equal to 2.6 divided by 9.8, which is a little bit more than 0.25.
0.265
Units?
seconds.
All right. So we know this thing is, ideally, it'll be in the air that long. Now back over to here. So I know the time, 0.2653 seconds. What is the force acting on the ball as it's in the air? Yes, and the formula for weight?
Mass times acceleration due to gravity.
And so it's the mass, whatever that happens to be, times g, and also negative. And that's going to be equal to, oh, wait a second. I apologize. This has been a fun exercise of going through some, trip down memory lane, but we're trying to find how far it went. Impulse momentum, not the way to go. Because just realize that what we're gonna show is that the change in velocity was negative 2.6 meters per second. Not particularly exciting since we just did that over there. Oh well, at least we recorded it. All right, so, well, we now have one other piece of information. If I want to figure out how far it went, using chapter 3 stuff, I know it's initially going 2.6 meters per second. It ends up going 0 meters per second. The time it takes is 0.2653 seconds. How do we find how far it went?
Average speed times time.
So what's the average? Oh, without a calculator. I believe in you. I think you can do the average without a calculator.
1.3.
I think someone just said it.
1.3.
Yes, 1.3. It's half of 2.6. All right, so my average velocity, 1.3 meters per second, which is just the average of 2.6 and 0. And so, and then we multiply that times the time, so 1.3 times 0.2653 meters per second in seconds. And what do we end up with? And a calculator would be easier on this one.
0.3449.
0.3449
Yep.
units. All right, let's find out how close we actually get. The ball was shot over there. There it is. Oh, yeah. Oh. Less than ideal, but hopefully my fingers are not going to affect it too much. That looked like 34 centimeters to me. We nailed it. All right, going to require good eyesight again. So it's going to be launched at, let's see, where is that on the meter stick? That's roughly, we go for the bottom of the ball, it's about the 36 centimeter mark. All right, here we go. I guess anyone who can see it well.
Below 70.
Divide to 70,
Minus 70, a little bit below it.
put it somewhere, I don't know where my finger is right now. So somewhere around there.
Yeah.
All right, so that's about 69 centimeters. So it went up to 69 centimeters. It started out at, I said 36 centimeters. So this was my initial position. So we established, let's go talk about position versus displacement. 0 was down here on the platform. This is my initial position. This is my final position. So my displacement, how far it actually changed from the beginning to the end, my displacement is 33 centimeters. And we had predicted 34.5. Not too bad. We're about 3% off or so. Better than most physics labs. Now you should just be absolutely amazed that a classroom demonstration ended up that close. Or you take more physics and then you learn to appreciate moments like that. Questions? That is not a good sound. So part of this is that it used to be I just moved the mouse in, it would come up, I didn't have to log in like I do now. So waiting for an exciting video. All right, so now I need to get volume. Let's see. I have to turn this crap on. There we go. That's what I wanted. I assume you could hear that.
No.
One of you might need a hearing aid. That sound the same or different than what I just played before?
A little bit lower.
It's a little bit lower,
Yeah.
It's a little bit quieter.
but quieter. We referring to lower frequency or lower volume?
Now the lower volume.
Lower volume, okay. I suspect that part of that was the less of a shock. All right, here's the first one. Here's the second one.
They're pretty the same.
Did anyone hear a difference? There was a difference. Here, let me play them at the same time. The fact that it was doing that when you played them at the same time, where you got that oscillation back and forth, that is an indication that they're not the same. Any of you ever seen a piano tuner actually tune a piano? It's probably a relic of the past. Surely there's some of them out there, especially since we have the School of the Arts here. But what they would do is that for a particular note, they know what frequency it's supposed to be, and so they would play that note on a tuning, used to be a tuning fork, they probably have automated things now, and then they would play the note on the piano, and they would be listening for that. And so as we get closer, so this will be closer, that is real close, that's the second one. The first one, I assume they sound pretty much the same to everyone here, except we can't hear it. Here's the first one, and here's the second one on top of it. So the fact that it took longer, that the oscillation was longer, that tells me that they're getting closer and closer. And if they're identical, then I guess mathematically they'd be an infinite distance away. Or it would oscillate over an infinite amount of time. And now, the first one, and then on top of that, I'm going to play one that's farther away. All right, so the first one, and then the second one that's farther away. All right, let's explore that. But in order to do that, I do need to get some props. So I'm going to grab some props. Pause this. Hear it. All right, so chapter, I guess 19 through 21. Never remember which is in which chapter. So the first frequency that I played over there was 440 hertz. That was the frequency. Again, that's the symbol. It's the same symbol I use for frequency is the same one I use for friction. There is in more advanced textbooks, there is a more standard symbol that is used for frequency. Unfortunately, it is this. It is the Greek letter nu, which looks a whole lot like a V. Matter of fact, in some textbooks, the nu looks like that. There's a reason I don't use nu, because it looks too much like a V. So we're using F for frequency. And so this is the number of oscillations per unit time. So it could be oscillations per hour or oscillations per whatever you want per year. Hertz specifically is oscillations per second. Now, if I wanted to represent this, so the sound, it's basically, it's pressure going in and out. So when it hits your eardrums, there's a slightly higher pressure, which pushes your eardrum in, followed by slightly lower pressure, which pulls your eardrum out, and then back and forth, and that transmits to a signal which most of us will hear. There's certain frequencies I can't hear, that you probably can. But at some point, age will catch up to you, and even if tinnitus doesn't get to you, you still lose hearing for some of the frequencies.
Dr. Fox, what does it say underneath oscillations?
SEC, that's second, oscillations per second. Now, typically oscillations isn't written, I think it should be, but it's not, so often, sometimes you will just see hertz is equal to 1/seconds. This is a hertz. Anyone want to take a wild guess who got honored by this thing? By this unit? Okay, I guess no one does. All right, so that was the first frequency. If I wanted to represent that, I would need to somehow represent high pressure, low pressure. I would represent it like that, where we have, this is sort of the ambient pressure. I think I pronounce it like there's an A there, but I think it's actually an E, or a little question mark. Pressure. And so this would be the high pressure, this is what pushes your eardrum in. I should say higher pressure, it's not like it's puncturing eardrum. And this is the lower one. So it just represented like a wave, similar to when we had sending pulses back and forth, Bradley and I were sending pulses back and forth. This, we could use the exact same diagram, except this would represent physically, if you took a snapshot of it, that the fact that it was, there was the center line, and then it's how far off it went off the center line. So I use the exact same symbol regardless of whether I'm talking about pressure or talking about physically what it looks like. Now, if I have a wave, so let's think about when we were sending pulses on the same side. So this is a physical representation of what we had out there.